lowering in vapor pressure. The addition of a non-volatile solute to a volatile solvent decreases the escaping tendency of the solvent molecules from the surface of solutions, as some of the surface area is occupied by non-volatile solute particles. According to Raoult's law, the relative lowering of vapor pressure is equal to mole fraction of solute. Thus, PA naught minus P upon PA naught is equal to XB, which is equal to NB upon NA plus NB. For a dilute solution, Na is much greater than Nb. Hence, neglecting Nb in the denominator, we have Mb is equal to Pa naught upon Pa naught minus P multiplied by Wb into Ma upon Wa.
Of binary solutions. We shall discuss the vapor pressure of liquids in liquids and solids in liquids. First, we will discuss a binary solution of two volatile liquids, 1 and 2, that are completely miscible in all proportions. In 1886, through experimental studies, a French chemist M. Raoult established a quantitative relationship between the mole fraction of a given component and the partial pressure exerted by it. The law states that the partial vapor pressure of each component in the solution is directly proportional to the mole fraction of it in the solution. Now, if P1 and P2 are the partial pressures exerted by the components 1 and 2 at a certain temperature, then, according to Raoult's law, P1 is proportional to X1, or P1 is equal to P1 naught X1, where P1 naught is the constant of proportionality and represents the vapor pressure of pure component 1 at the same temperature. Similarly, for the component 2, P2 is equal to P2 naught X2, where P2 naught represents the vapor pressure of the pure component 2. Now, if you apply the Dalton's law of partial pressure, the total vapor pressure of the mixture would be equal to the sum of the individual partial pressures of the component 1 and 2. That is, P total is equal to P1 plus P2, or P total is equal to X1 P1 naught plus X2 P2 naught. Let this be equation number 1. Further, you know that for a binary solution, the sum of mole fractions X1 and X2 is equal to 1. Or, we can write X1 equal to 1 minus X2. Now substituting for X1 in the equation 1, we get P total is equal to 1 minus X2 P1 naught plus X2 P2 naught. Let this be the equation 2. In the equation thus obtained, we can see that P total is a linear function of mole fraction X2 as P1 naught and P2 naught are constant at a particular temperature. If a graph is plotted for the partial vapor pressure of the first component against the mole fraction, corresponding to the equation P1 is equal to X1 P1 naught, then a plot as shown here is obtained. As you can see in the graph, when the mole fraction of first component becomes 1, the partial pressure of component 1 is the vapor pressure of the pure component 1. Similarly, a plot for the component 2 corresponding to the equation P2 equal to X2 P2 naught on the same set of axes is represented as shown here. Now, as can be seen from the curve, the vapor pressure of the pure component 2 is higher than that of the pure component 1. This means that the component 2 is more volatile than component 1. Now the total vapor pressure of the binary mixture P total is given by the sum of the partial pressures P1 and P2. As you can see in the diagram, the solid straight line gives the plot of P total versus mole fraction. Further, as the vapor phase is in equilibrium with the solution phase, the composition in the vapor phase can be determined by the partial pressures of the components by the equation P1 is equal to Y1 P total and P2 is equal to Y2 P total, where Y1 and Y2 are the mole fractions of the components 1 and 2 respectively in the vapor phase. It is important to note that the above holds true only if the two components in the binary solution are volatile and are completely miscible with each other. Now, if one of the components in the binary solutions is considered to be highly volatile, such that it exists as a gas, then, as you know, its solubility is given by the Henry's law. P is equal to KHX. As can be seen from the equation, the partial pressure P of the highly volatile component or gas is directly proportional to the mole fraction X, and KH is the constant of proportionality which can be equated to P naught. In other words, we can say that Raoult's law is a special case of Henry's law. Let us now discuss the vapor pressure of binary solutions of solids in liquids. That is, Raoult's law for non-volatile solutes. A non-volatile solute has no tendency to form vapor at the temperature of the solution, and it will therefore not contribute to the total vapor pressure of the solution. For example, in a solution of salt in water, salt is a non-volatile solute and does not contribute to the total vapor pressure of the solution. Thus, the vapor pressure of the solution will be the vapor pressure due to the solvent only. That is, P total is equal to P1 or P total is equal to X1 P1 naught, where P1 naught is the vapor pressure of the pure solvent at a particular temperature and X1 is the mole fraction of the solvent 1. On the basis of Raoult's law, the liquid solutions can be classified into ideal and non-ideal solutions. Let us first discuss the ideal solutions. A solution that obeys Raoult's law over the entire range of concentration is said to be an ideal solution. For an ideal solution, the enthalpy of mixing and the volume of mixing of the pure components are zero. This implies that no heat is evolved or absorbed, and also there is no change in volume on mixing of the two components. For example, if 50 ml of hexane is mixed with 50 ml of heptane, the volume of the solution obtained is exactly 100 ml, and no heat is evolved or absorbed in the process. At the molecular level, the ideal behavior can be explained in terms of the intermolecular attractive interactions between the two components. If A and B are two components, then in an ideal solution, the magnitude of A-B interactions will be same as the magnitude of AA and BB interactions. However, in real life, there is actually no such thing as an ideal mixture, but some liquid mixtures get fairly close to being ideal. These are mixtures of two very closely similar substances. Some common examples of mixtures that show nearly ideal behavior are hexane and heptane, benzene and methylbenzene, chloroethane and bromoethane. Since ideal solutions obey Raoult's law, they show the graphical behavior as shown here. Let us now discuss non-ideal solutions. Solutions that do not obey Raoult's law over the entire range of concentration are said to be non-ideal solutions. Non-ideal mixtures produce curves rather than straight lines as shown here. The dotted straight lines represent the ideal behavior and the curved lines represent the deviations from the ideal behavior. The reasons for the deviation are the intermolecular interactions at the molecular level. For a non-ideal solution, the magnitude of AB interactions is not same as the magnitude of AA and BB interactions. Also, delta H mixing is not equal to 0 and delta V mixing is not equal to 0 for such solutions. If the magnitude of AB interactions is weaker than the magnitude of AA or BB interactions, then this implies that such solutions have a higher tendency to escape in the vapor phase and will show a higher vapor pressure. Such solutions are said to exhibit positive deviation from Raoult's law. The total vapor pressure of such a solution is greater than the vapor pressure corresponding to the ideal solution of the same composition. For example, a mixture of ethanol and cyclohexane shows positive deviations from the Raoult's law. Ethanol exists in highly associated form due to hydrogen bonding. On addition of cyclohexane, its molecules get in between and there is a considerable reduction in ethanol-ethanol hydrogen bonding. As a result, it becomes easier for the ethanol molecules to escape into the vapor phase, and thus we see the positive deviations from the Raoult's law. For a positive deviation, delta H mixing is greater than 0 and delta V mixing is also greater than 0. Methyl alcohol and water, carbon tetrachloride and chloroform are some other solutions that exhibit positive deviation from the Raoult's law. On the other hand, if the magnitude of AB interactions is greater than the magnitude of AA or BB interactions, the escaping tendency of A and B type of molecules decreases and the partial vapor pressure of each component decreases. This in turn results in the decrease of the total vapor pressure of the solution. Such type of solutions are said to show negative deviations from the Raoult's law. As you can see here, formation of a H bond takes place between the chloroform and the acetone molecule. This decreases the escaping tendency of the individual molecules and results in negative deviation from Raoult's law. For the solutions exhibiting negative deviations, delta H mixing and delta V mixing both are negative. A few more examples of non-ideal solutions exhibiting negative deviations are phenol-aniline and chloroform diethyl ether solutions. A detailed look at the two graphs show that there are some large deviations from ideal behavior at specific compositions. These very large deviations from ideality form a special class of mixtures known as azeotropes or constant boiling mixtures. Azeotrope is thus defined as a special class of liquid mixtures that boil at a constant temperature and at a certain composition. At this condition, the mixture behaves as if it was a single component with one constant boiling point. In such cases, it is not possible to separate the individual components of the mixture by...
Okay students, here let's start saying relative lowering of vapor pressure. What is mean relative lowering of vapor pressure? It means suppose I am taking a pure solvent. This pure solvent is when I boil the solvent, some vapor pressure is generated. The vapor pressure is nothing but dependent upon only solvent molecule. Clear? So for this solution is the for the solvent, I add small amount of sugar. When I add, look at the area for the boiling and evaporation in the surface. Evaporation surface. So here number of solvent molecules are more amount of the particles will be evaporated, more amount of the pressure will be generated in the solution. Suppose if I add this non-volatile solid means the solid which cannot be easily vaporized. So what happens, the surface area is covered with the non-volatile solid particles. You can easily notice here that most of the area is covered with non-volatile solid particles. So escaping tendency of the solvent molecule from surface area decreases. So the pressure will decrease. That is nothing but a relative lowering of vapor pressure. Clear? What I mentioned, when non-volatile solute is added to a solvent, the vapor pressure is solvent is lower. Clear is there? No, here free all water molecule will evaporate because of solvent particles, non-volatile surface area reduces, so the tendency of reduces. What you want to hear the when compare with this one, in this one how much percentage of vapor is reduced? Nothing but a relative lowering of vapor pressure with respect to non-volatile solute. Based on the amount of non-volatile solute is there, here the much amount of the vapor pressure will be reduced. That's called as a relative lowering of vapor pressure. So go for next slide here. Look at the for an ideal solution. For an ideal solution of non-electrolyte, because the vapor pressure of the solution is followed Raoult's law. The vapor pressure of the solution is here P equal to the mole fraction of the X multiplied by the vapor pressure of the pure solvent. Already we discuss here pH in the solvent vapor pressure is equal to vapor pressure of pure solvent and small fraction. Clear? If suppose if I am taking here, you look at relative lowering of vapor pressure. I already discussed in the previous session is there, no? Here only pure solvent molecules are there. Suppose I am taking here the pure solvent molecules are there. We have here vapor pressure is pure vapor pressure is taking the vapor pressure of the K P naught. Look at it, P naught, and actually is the P naught here A into mole fraction of the A. Clear? Yeah. This is nothing but here. This is nothing but a P A. Total pressure of the solvent molecule. Here, consider if you add non-volatile solute is there, no, here P total value. P total value, total pressure is here. Solvent molecule, imagine is a P solvent molecule I am taking as a PB. PB is equal to the, you know very well, is equal to the P naught B is equal to the P naught B into XP. Clear? P naught B into XP. P total value is equal to here, look at there is depend upon the PA plus PB. Okay, PA plus PB. You know very well here, just one point remember, you know, the here solute is non-volatile, so it cannot produce any vapor pressure, so it can be cut this one. So P total value is equal to P total. Look at I mentioned here clearly, P total value is depend upon only vapor pressure of the solvent only. Vapor pressure of the solvent only. Okay, and you can also write here P total value is equal to, I mentioned here clearly, P total value is equal to P total is equal to P naught A, clear, P naught A XA, clear, total value is equal to P naught A XA. So this one you are going to follow it is very clear, no? So go for next slide is there, no? You can easily find here the vapor pressure is reduces. The vapor pressure is reduced. How much you look at the reduces here? Look at the vapor pressure of pure solvent. Then compare with the vapor pressure of pure solvent is there, no? Then look at the use of the vapor pressure of the pure solvent. These are the vapor pressure of the pure solvent. Look at here. It takes one is here. I'm just taking here. The one is the vapor pressure of the color level take. Okay. This is the vapor pressure of the pure solvent. What happens when a complete solution is a solution? So what if the solution vapor pressure always less than the vapor pressure of pure solvent only, no? So what is there here mentioned? Delta P. If you mention is delta P. What is delta P? Change in the vapor pressure. What change in vapor pressure? Delta P equal to here P naught A. Look at P naught A. Pure solvent vapor pressure is more. Pure solvent vapor pressure is more. P naught A. Here solution vapor pressure. PA after mixing of solution. PA. I want to calculate how much percentage of the vapor pressure reduces with respect to pure solvent only. So what is the relative lowering? This function is the RLVP. This function is the RLVP. Okay, relative lowering vapor pressure. What is here when compared with the delta change in vapor pressure by delta P by P naught of A directly proportional to number of moles of solute, you know. Solute I am taking is XB, number of moles of the solute. Clear? So suppose the mention is the look at I want to remove the proportional constant here. So what I mean here mention delta P, okay, delta P by P naught A. Boiling point, you know, constant will take over. Boiling point is called Kb. This is called Kb. It's directly proportional to the mole fraction of Xb. Clear? Mole fraction of the Xb only. So remember this called Kb is called elevation in the boiling point only. First one is called as a elevation in the boiling point. What they mention, you know very well here. You know very well. XA plus XB equal to 1 only, no? XA plus XB is equal to 1. Clear? XA plus XB is equal to 1. XA is equal to XA is equal to 1 minus XB. Clear only, no? 1 minus XB. Sorry, 1 minus XB. Remember. So when I substitution here, look at the otherwise mention is XB is equal to sorry, okay, XB is equal to 1 minus XA. Can I substitute XB value, no? Here XB value, no? XB nothing but 1 minus XA. So remember here P nothing but vapor pressure of solution, P naught vapor pressure of the pure solution, Xn nothing but mole fraction of solution, Xp nothing but a mole fraction of the solute only. Here solvent, Xa nothing but solvent, here Xp is solute. This called as a relative lowering. When compared with the pure solvent for solution, how much pressure reduces? You know very well here. One point I want to remember, you just remember mole fraction of Xp is equal to mole fraction of Xb, you know very well, Xb is equal to number of moles of A by, look at the number of moles of A by number of moles of A plus number of moles of B. Do you know very well here, no, when you get the given EFF solvent, if your function is number of moles of B, sorry, number of moles of B by number of moles of B by number of moles of A plus B. For a dilute solution, is there, no, here in the denominator position, when compared with the Na value is here more, very more. Okay, Na value is more, though more than the Nb, more than the Nb. So we can neglect the Nb value. We can neglect the Nb value in the denominator. So what will get neglect denominator here? Look at here, what will get here? Look at here, the mention is, okay, look at here, mention is P, look at here, mention is P naught A minus PA, P naught A minus PA by P naught A, here P naught A is equal to constant letter N B by Na only, no? NB by Na. Clear? So what is the NB value? How will you get NB value? Number of moles of B. Could I mention nothing but a weight of solid mention is B by molecular weight of solid only, MB. Clear? So Na is equal to what is Na value is equal to weight of A by molecular weight of A only. So if they have taken solute is, they will take as a N2 also, no problem. If solvent is N1 also taken is no problem. Okay, clear, no? So go for the next slide here, look at very clearly. Okay, here look at the sorry, the absolute lowering vapor pressure is equal to P naught A minus PA is equal to delta P. There is nothing but change in the vapor pressure. The change in the vapor pressure is equal to the number of moles of solid particles and vapor pressure of the solvent only. Remember, delta P directly proportional to change in vapor directly proportional to the number of moles of the solid particles. That's called lowering of vapor pressure. Delta P nothing but a lowering of vapor pressure. So if you consider the lowering of vapor pressure, we will go for next slide. Look at very clear. So I'm taking here. Look at they given one problem out there. So look at there. Calculate the lowering vapor pressure of a solution. Then 50 grams of dextrose again. 50 grams of dextrose. Molecular weight is 180. It's like glucose only. So it is present in the 1000 grams of the water. Water molecular weight is given. The vapor pressure of the water is the main vapor pressure is the given. This one is solvent vapor pressure is the given. How can be calculated? What is the formula? Look at this is the formula. This is the formula. Clear? So number of moles of the water molecule. How many moles of water molecule? How much given here? The given is then 50 grams of glucose present in the 1000 grams of the 1000 grams. Look at here solvent weight. Solvent is the Na. Na weight is given. How much is given? Na weight is 1000 grams. 1000 grams. Okay, number of moles someone will get the by 8. How many moles you will get? 55.5. This is value is 55.5 will come here. Next number of moles of solid molecule is given. How much weight is given? 50 weight. 50 means number of moles of solute. Nb is equal to number of moles of solute. Nb is equal to what is weight is given here? How much weight is given? 50 grams. 50 grams by 180. Clear, no? How many moles are getting here? Look at the 0 0 will cancel. 5 by 8. How many moles are getting? 0.278 moles of the dextrose is coming. Mole fraction they are asking. Mole fraction of what is there here? Number of moles of B by number of moles of A only. Number of XB is equal to they are asking XB is equal to number of moles of B by number of moles of A. What is number of moles of B here? Number of moles of B, how much you got? This is nothing but number of moles of A. Number of moles of A, this is nothing but number of moles of A. So what is the here? Look at the calculated number of moles of solid plus number of moles of solvent they have taken. Mole, they will get the mole fraction. Become mole fraction Na plus Nb only. So here Nb only, sorry, Na plus and Nb. So what will get the 0.0478. Vapor pressure, what is the mention here? Vapor pressure the mention. Vapor pressure, how much you change the vapor pressure value? So XB into mole fraction. So already they given this value here. The mention is the vapor pressure is the mention. So here we look at the vapor pressure is the mention and mole fraction is the mention. So what you'll get the 0.078 millimeters only get. So 0. So with this one you get clear idea. Okay, from this one you can calculate the. Once again I'm saying here they're asking about this value, how much change in the vapor pressure. This value you have to calculate. This value is already given. How XB value come is XB nothing but here a mole fraction of XB nothing but a, okay, NB by, okay, na, NB by NA plus NB, NA plus NB. It's nothing but a mole fraction of B. Calculate, you'll get idea. Okay, thank you students.